So till now we had done how to solve a higher order differential equation with constant coefficient. Okay. Now we will see how to solve if coefficients are not constant. But for that again we are going to study only some particular type of differential equation. Okay. So today we are going to see Cauchy's homogeneous linear differential equation. Okay. So we can say a differential equation of the form okay, so this is some particular type of differential equation which is of the form an x raised to n nth order derivative of y with respect to x plus an minus 1 n, and it goes on till a2x square d square y by dx square plus a1x dy by dx plus a naught y is equal to x. Okay, so here you can see the coefficients, okay, of this differential operator are x raised to n. This is the nth order derivative and the coefficient is x raised to n. This is the n minus the 1th order derivative and the coefficient is x raised to n minus 1. Okay, this is second order derivative, the coefficient is x square. First order derivative, the coefficient is x. Okay, so in this case the coefficient of this differential equation are not constant. It's not constant but it hits with some function of x. Okay, where this a naught, a1 till an are usual notation, so where we can say ai is constant for all I and x is some function of x only. Okay, so this is our usual notations. Okay, now to solve this type of differential equation, say this as 1. Okay, see, we don't know how to solve this type of differential equation. We know how to solve a differential equation with constant coefficient. Okay, so we will take such substitution. This differential equation will equation 1 will be converted to the differential equation with constant coefficient. Okay, so we can say such equation can be reduced to differential equation with constant coefficient. Okay, so for that we are going to take a substitution by substituting x is equal to e to the power z, or we can say z is equal to log of x. So you can say either we can say z is equal to log of or we are going to substitute x is equal to e to the power z. But if I going to replace x in terms of z, then I need to replace this differential operator also in terms of z. Okay, so let's find out dz by dx, that we can find easily, which is what, 1 by x. Now what we have to replace? Okay, I have replaced x in terms of z, so definitely I need to replace this operator dy by dx also. So let's consider dy by dx. Okay, so now we can rewrite this is by using the chain rule, dy by dz into dz by dx, and we know dz by dx is 1 by x into dy by dx. Okay, so what I'm getting, this gives me, if I multiply this throughout by x, I will get x dy by dx, sorry, this is dy by dz, okay, is equal to dy by dz. Okay, and this we can rewrite as d into y. But in the previous lectures my d was d by dx, but in this case here my d is differentiation of y with respect to z. So we can say, where this is the important, you have to remember d is what, it is derivative with respect to z. Okay, it is a derivative with respect to z. Okay, so this is for first order, dy by dx, then it is equal to 1 by x dy by dz. So we can replace x into dy by dx is equal to dy, where d is dy by dz. Now on the similar line we can replace d square y by dx square also. So we can rewrite this as d by dx of dy by dx. So dy by dx we have find already over here. So d by dx over 1 by x into dy by dz, right? Okay, so now let's use u into v rule, because it may be also some, after differentiating with respect to z, this may be also some function of x. So let us use u into v ka rule. So we will get this is equivalent to 1 by x into derivative of this with respect to x. So we can say this is d square y. Again we are going to use a chain rule. So d square by dz square into dz by dx plus dy by dz now as it is, and we are going to differentiate 1 by x. So it is minus 1 by x square. So we can rewrite d square y by dx square is equal to, so this is equivalent to dz by dx is 1 by x. So 1 by x into 1 by x gives me 1 by x square, d square y by dz square minus 1 by x square dy by dz. So this is equivalent to, if I multiply this throughout by x square, then we will get x square d square y by dx square, which is my required thing. Okay, so x square d square y by dx square is equivalent to d square y by dz square minus dy by dz. Now we can replace it is in terms of d. So we will get it is d square minus d over y, or we can rewrite this as d into d minus 1 of y. Okay, on the similar line you can find it is for the third order derivative. Okay, so we can say similarly we can find dx cube d cube y by dx cube is equal to, see what is here, dy. This is d into d minus 1y. So then next will be d into d minus 1 into d minus 2 of y, and this process gone on. And so on. Okay, so if I have, suppose we need to find x raised to 4, d raised to 4 by dx raised to 4, then this is equivalent to d minus 1, d minus 2, d minus 3 over y. But my d is what? D by dz. Means what? After taking this substitution, we are going to replace x dy by dx, x square d square y by dx, x raised to n minus 1, d raised to n minus 1 by dx raised to n minus 1. Means whatever differential equation will remain after substituting, that will be a differential equation with constant coefficient. So that we can solve by our usual way, which we have done in the previous lectures. Okay, now let us solve one question. Okay, so here we have some second order differential equation. Now let us see, this is not a differential equation with constant coefficient, but what are the constants? See, this is the second order derivative, the coefficient is x square. This is the first order derivative, the coefficient is 3x, means x dy by dx. So it is in the Cauchy's differential equation form. Okay, so let us take a substitution. See, whenever you are going to solve this type of differential equation, you must have to write the substitution which you are going to take. So we are going to take x is equal to e to the power z. So my z is equal to log of x. Okay, so there is no need to write the full procedure, but at least you have to write the important steps. Okay, the proof is not required, but you have to write the important steps. Okay, so now we can say x dy by dx, this is equivalent to d of y. This we have done in the previous slide. Okay, now similarly we can write d square x square d square y by dx square is d into d minus 1 of y. But what is d? D is now differentiation with respect to z. So this is important. Whatever answer you will get, that will be in terms of z. It is not in terms of y, because we had replaced x is in terms of z. Okay, so now we can write this differential equation as d minus 1 of y minus 3 d of y plus 5y sine z. Okay, we will simplify it more. D square minus d minus 3d plus 5y is equal to sine z. So this is equivalent to d square minus 4d plus 5y is equal to sine z. Now see, this is a differential equation where the coefficients are not constant, but after taking substitution, whatever differential equation I am getting, that is with constant coefficient. But remember, here my d is d by dz, so whatever answer I am going to write, that will be in terms of z. Okay, so now we can solve this easily. Okay, we know the general solution of this type of differential equation is addition of complementary function and particular integral. So you can find the roots of complementary function. So the auxiliary equation is d square minus 4d plus 5 is equal to 0, and the roots of auxiliary equation are 2 plus or minus I. Okay, so these are the complex roots, okay, where alpha is 2 and beta is equal to 1. So you can write yc is equal to e to the power 2z. Okay, because this is the d by dz operator. So e to the power 2z into c1 cos z plus c2 sin z. Now you can replace z in terms of x. So e to the power z is x. So e to the power 2z will be x square c1 cos of log x plus c2 sin of log x. So this is my required complementary function. Now we can write particular integral, which is 1 by d square minus 4d plus 5 over sin z. Okay, so this we can solve easily. What is the rule? We have to replace d square as minus a square. In this case, a is 1. Okay, so we have to replace d square as minus 1. Okay, so let's replace it. Minus 1 minus 4d plus 5 over sin z. So this is equivalent to 1 upon 4 minus 4d over sin z. So let us take 1 by 4 outside, which is the constant, and the remaining thing is the sin z. Okay, so now here we cannot use the shortcut method for sin z because it is only valid for the d square cut term. So here I don't have d square cut term. So what we can do, we will divide and multiply by 1 plus d. Okay, so 1 by 4 divide and multiply by 1 plus d. So we will get 1 plus d upon 1 minus d square over sin z. So now first of all we will apply sin z on this operator. So we will get 1 by 4 1 plus d. Now replace d square as minus a square. That means we have to replace d square as minus 1. So we will get 1 plus d, 1 upon 1 minus of minus 1 of sin z. Oh, I'm sorry, this I had written twice. Okay. Okay, so now we will get 1 plus d 1 by 2 sin z. Let us take 1 by 2 outside. Okay, so now apply sin z on the remaining operator. So we'll get 1 by 8 sin z plus d means d by dz of sin z. So I'm getting particular integral as 1 by 8 sin z, derivative sign is cos z, cos z. Now replace z in terms of x. So 1 by 8 sin of log x plus cos of log x. Okay, so now we are able to write the required general solution, which is y is equal to yc plus yp. Okay, so it is equivalent to x square c1 cos of log x plus c2 sin of log x plus 1 by 8 Okay, so this is the required solution of the given differential equation. Okay, so now let us solve one more question. Okay, now let's consider this differential equation. See, now I have third order differential equation. Okay, where the coefficients are not constant. But what are the coefficients? See, it's a third order derivative, the coefficient is x square. The second order, the coefficient is x. Okay, it's the first order, the coefficient is 1. But if I want to compare it with Cauchy's differential equation, see, what are the coefficients? dy by dx के साथ x का term should be there. For second order there, x square का term should be there. So for third order, x cube का term should be there, right? Okay, so to make it is to Cauchy's differential equation form, we will multiply this by x. So we will get x cube Okay, so now this is the Cauchy's homogeneous differential equation. Okay, see, this is not in the proper form, right? But after multiplying, this becomes the Cauchy's homogeneous linear differential equation. Now the procedure is again same. Take x is equal to e to the power z, where z is log of x. So we can replace x dy by dx as dy, x square d square y by dx square as d into d minus 1 of y, x cube d cube y by dx cube as d minus 1 d minus 2 of y. Okay, so this, but my d is d by dz. Okay, so now let us rewrite the given differential equation in terms of z. So we will get d minus 1 d minus 2 of y plus 3 d minus 1 of y plus dy is equal to x is e to the power 3z, e to the power z, so it is e to the power 3z, log x is z. Okay, so now we can simplify it. So it is d square minus d minus 2 plus 3d square minus 3d plus d over y is equal to e to the power z into z. So let's multiply it. D cube minus 2d square minus d square plus 2d plus 3d square minus 3d plus d over y equal to e to the power 3z into z. Okay, so this is cancelled. This is also cancelled. So the remaining thing is d cube of y e to the power 3z into z. Okay, so now you can solve this easily. This is the our apna normal differential equation with constant coefficients. Okay, so you can find the roots of the complementary function. D cube is equal to 0. That means 0, 0, 0. It's repeated 3 times. So we can say yc is c1 plus c2z plus c3z square over e to the power 0z. Okay, so now let us replace z in terms of x. So we will get c1 plus c2 of log x plus c3 of log x the whole square, and anything raised to 0 is 1. So this is my required complementary function. Now let us find out particular integral. So it is equivalent to e to the power 3z into z. Okay, so now you can use 1 upon f of d into e to the power x into b ka rule, right? Okay, so we can say e to the power 3z will come outside and f of d becomes f of d plus a. Here a is 3, that means d becomes d plus 3 ka cube to z. So this is equivalent to, let us open it. So d cube plus 9d square plus 27d plus 27 for z. Okay, so now the right hand side function is z. So we will apply 1 upon f of d into x ka rule. So for that we have to take the lowest degree term outside, which is what? 27. So let us take 27 outside. Okay, so we'll get it is equal to 1 plus d cube plus 9d square plus 27d by 27 over z. Now we will expand this by using the series expansion of 1 upon 1 plus x. Okay, but the right hand side is z. Okay, the first order derivative is 1, second order derivative is 0. Right? Okay, so we will expand this is still first order derivative. Okay, first order. We are not going to take higher orders because the derivative vanishes. Okay, so e to the power 3z by 27, 1 minus d cube plus 9d square plus 27d by 27 plus minus so on over z. We are not going to write the higher orders because the derivative vanishes. Now let us see. 3z by 27. 1 minus, see, d cube over z, the third order derivative, which we don't want because it goes 0. Second order derivative is also vanishes. So the remaining part is 27d by d, which is just d over z. So let us simplify it. Okay, so z minus d by dz of z, that means first order derivative. So it is just z minus 1. Now replace z in terms of x. What we have taken, x is e to the power z. So e to the power 3z is x cube by 27z is log x minus 1. So this is my required particular integral. So at last we can write the general solution, which is addition of complementary function plus particular integral. Okay, so this is the required solution of the given differential equation. Okay, now let us solve one more. Okay, now let us see this differential equation. See, here we have the operator d by dx plus 1 by x the whole square over y is equal to 1 by x raised to 4. So this is not in the proper higher order differential equation form. So first of all, we will try to make it. So this is the operator which I am going to operate twice. So we can say d by dx 1 by x, d by dx plus 1 by x over y is equal to 1 by x raised to 4. So now first of all we will apply it on y. So we will get by x raised to 4. Now apply this on this remaining operator. So we will get d by dx or dy by dx plus y by x plus 1 by x to dy by dx plus y by x is equal to 1 by x raised to 4. Okay, so now we can solve it. See, we will get d square y by dx square and d by dx of y of x. See, y may be some function of x and x is again some function of x. So you can use u into v ka rule. So we will get it is equal to 1 by x into dy by dx plus y into minus 1 by x square. Okay, similarly here 1 by x